We are looking at 9.1. This is in Chem124.
You can't just ignore them. I mean, I guess they
We're looking at 9.1, number 2. And this is really number 2, 3, 4, and 5, if memory serves. Where it's asking a bunch of questions about, we've got this NH3 plus O2 reaction producing nitrogen monoxide, and we've got 2 grams of NH3, 4 grams of O2. I start with, and I'm doing this my particular way, a couple people were doing different things. I start with converting to the grams to moles using molecular weight. That gets me the moles of each thing. Now the catch is, normally I'd do a pretty good job of eyeballing something and telling what the limiting reactant is. With these, this one's going to be limiting. I actually can't eyeball it, but let's actually do the calculation. The way I can eyeball it is because these are pretty close to each other. Actually, no, I can't eyeball it. Let's do the calculation to be sure. When they're this close and the coefficients are that close, it's like hard for me to tell. The fact that this is bigger tells me I want more O2 than NH3, but I have a little bit more O2 than NH3, so I can't really tell. So I'm going to do a little side calculation to figure out which one is limiting. And the way I do this is I do a calculation of total moles of reaction possible. So I take my 0.1176, I'm going to do it over here, I think I'm blocking the camera. I take my 0.1176 and I multiply by one reaction, has 4 moles of NH3, and I get a number. And I do the same thing. That would be how many reactions can happen with my NH3. I do the same thing with my O2, 0.125, where one reaction is going to have 5 O2s used in it. I calculate those two things, and the smaller number is the smaller number of reactions is the thing that limits the reaction. 0.125 divided by 5. Oh, that's not the number I was expecting. Did I type that in wrong? 0.125 divided by 5. There we go. I typed it in wrong. 0.025 reactions. And that's 0.025 moles of reactions. You can't have a fraction of a reaction, but this should be all moles. And then 0.1176 divided by 4 gets me 0.294. So, turns out the O2 is slightly limiting. So I'll go ahead and put a label on here so I don't forget. That's my limiting reactant. And now I can get back to doing my stoichiometry. So I'm going to erase this part in orange for figuring out which one is limiting reactant. There's places where it's going to come up again, but I'm just going to redo it all just to make sure I don't mess anything up and forget anything. So figuring out the limiting reactant is kind of a side problem from doing the real stoichiometry. Make sure I didn't make any mistakes. This divided by 4 is like a third. This divided by that is about a quarter. Yeah, that looks okay. Okay. Now I can go back to my stoichiometry. I start with these things. I start with no nitrogen monoxide, no water. And I do this in a table way, which I think we're finally getting comfortable with in my class. My 129 class is finally getting comfortable with it as well, because they didn't get my way of doing it, because they didn't have me for Gen Chem, like earlier. And now they love it too. I'm telling you, everyone should be doing stoichiometry this way, but we'll get there.
Which way?
The table way.
I never did it that way.
That helps.
You had me.
Yeah, I've never done it like that.
You don't have to, but it's like, I like it for a lot of reasons. So this allows us to think about where's it restarting, when this starts to mix together, as this arrow happens, what reaction is, what's happening during the reaction step, and then where do we end up actually. So the starting step is done. That's what we're starting with our mixing. The reaction step is going to be subtract the limiting reactant from the reactant side, add the limiting reactant to the product side. Our limiting reactant is the O2, so I'm going to have minus 0.125, minus 0.125, plus 0.125, plus 0.125. But we're not done. We need our mole ratios in there. So I got to multiply everything by mole ratio. And this is part of why I like this. I can think about how the reaction is proceeding all at once. Reactants getting used up, products getting created. Coefficient on the bottom of all of my fractions is always the coefficient of the limiting reactant, so I can put that 5 for the O2 in. And you'll notice technically I just recalculated the number of times the reaction happened again.
I don't know.
Right? If there was a 1 on top of each of these, that would be times the reaction happened. Now, each time the reaction happens, 4NH3 is used up. So I put a 4 on top. Each time the reaction happens, 5O2 is used up. So I put a 5 on top. Each time the reaction happens, 4NO is produced. Each time the reaction happens, 6H2O is produced. Now I've got 4 meth columns. So the thing that I like about this is we're kind of doing, this is not the way the problem is set up on LabPal, and we might be doing more work than LabPal is asking us to do, but we're kind of answering everything that could be asked about this stoichiometry problem at once. For me, it's faster, it's more organized, I'm less likely to make mistakes as long as I don't forget my mole ratios. That's the one thing I even still do. Sometimes I forget a mole ratio, I'm like, why is this wrong? It takes me like 10 minutes to figure it out. Okay, so then we go ahead and we do our calculations. This one should be 0 because it's the limiting reactant. It should run out. 129, folks, we know it's not really 0. We could do an equilibrium calculation to figure out how much O2 is left in the container.
You can.
127, folks, it's approximately 0. I'm going to calculate my moles of products because that's looking pretty easy to calculate since it's 0 plus. 0.125 divided by 5 times 4 is 0.1 here, 6, and 0.15 here. And again, part of this organizational thing lets me be a little bit lazy with my units. I'm not done yet. I still got anything to go here. Right, so this should be moles of NO, and this should be moles of H2O. Right, each column is all at, as long as I remember my mole ratio, this column is moles of nitrogen monoxide plus moles of nitrogen monoxide produced gives us total moles of nitrogen monoxide produced. In 124, we almost always have 0 reactants, or sorry, 0 products, and so it's always 0 plus. In 129, of course, we've seen the situations with common ion effect and buffers where we have non-zeros in our products. Not a worry for them yet. It's for you all later, right? There are situations later on in chemistry where those are not zeros. But for us right now, yeah, it's almost always 0 products to start. So right now, the 0 plus is redundant. You know, like adding 0 to something is pointless. But in the future, it's not always 0. The last thing I need to calculate real quick is I need to calculate how much NH3 I have left over. This will also be the point that tells me if I selected the correct limiting reactant. If this number comes out negative, I've made a mistake. Redo the whole problem again. So hopefully it doesn't come out negative. 0.125 divided by 5 times 4 negative plus 0.1176. Nope, we're good.
Keep your file up.
I've got some excess NH3 left over.
I think Marisa has.
Now this should give us, I've done too much. So now let's look at, okay, what did number 2 actually ask us to do?
What mass of nitrogen monoxide can be produced?
I'm going to take my 0.1 times the molecular weight, right? Because I've got it in moles. So I can finish off that part number 2 would be take this 0.1 times the molecular weight of nitrogen monoxide, 17 plus 16, that's going to be times 30. That's going to be 3 grams. I didn't even punch it in my calculator. I can do math in my head. What's number 3 ask?
What's the mass of water that can be produced?
I'm going to take this 0.15. Number 3 is going to be done over here. I'm going to take that 0.15 times the molecular weight of H2O. 0.15 times 18. And I get 2.7 grams. What's number 4 ask?
What mass of excess reagent remained after the reaction runs to completion?
I'm going to take this NH3, I'm going to multiply by the molecular weight again. And I'm going to get 0.299 grams left over. So only a little bit left over. So you could have done this where you did 4 separate calculations, right? Where you do You still have to identify limiting reactant, but you could do each column of math, right? I've got this set up, so it's just 0 plus this times that equals that number, right? I'm just doing math in columns like we did in grade school. And I like that here because it has this nice organizational kind of aspect. The reason we switch from doing, like in grade school, the reason we learn to do math this way first is because it's easier. It lines things up better. It helps us organize our thinking around the math happening. Same thing is true here. The reason we switch to doing math in our lines is more space efficient, right? It's more space efficient for the problems. You can fit more problems on a page that way. And they're like, you know enough that you don't need that. For me, this organizational kind of lining things up thing is always easier. The one thing you have to be careful about as you move on to future classes, don't get stoichiometry tables confused with equilibrium tables. They're different things. Part of the reason I like doing this is because this naturally leads us to doing equilibrium tables, but the units are different and the purpose of them is different, so you have to be careful about that. But getting used to this kind of organizational phenomena makes it really easy to do equilibrium tables because everyone does equilibrium tables that way. No one does equilibrium tables in single lines. Wait, do you? You smile at me.
No.
Okay.
I have a question on number
Sure.
6.
Sure, what's number 6?
It's really the same problem, but it says if 1 gram of water is produced, what is the percent yield? I didn't know what.
Oh, wait. May I see that question? That seems weird.
I got 36, or almost 37%. Because their actual is 2.7.
Yeah, I just wanted to make sure all the other numbers were the same.
Oh, you divide it using what we.
Yeah. So what we've done on the board here is theoretically what would happen if we did this perfectly. Realistically, the reaction is not going to be perfect, and they're like, hey, we didn't actually get 2.7 grams of water because the reaction didn't actually go through the entire completeness, or like something side happened, or like it just didn't happen the way we thought. We only get 1 gram of water. So if we get 1 gram of water instead of our 2.7 grams, like if we got 2.7 grams, we got everything we were expecting. That's 100% yield. If we got, let me do a quick math thing. If we got 1.35 grams, we only got half of what we were expecting. If we only got 1 gram, we do 1 divided by 2.7 times 100 to get percent yield. 1 divided by 2.7. So that gets us 37.03% yield. You had it.
So we don't have to divide it by the actual again?
No, so this is not percent error, this is percent yield.
Okay.
Right? So if we wanted to do percent error, we do 1 minus 2.7 divided by 2.7.
Okay.
If we're doing percent yield, it's just the fraction of how much we got divided how much we should have gotten.
Okay.
That's percent yield.
I had a question on 9.2. It's kind of like, I guess, 2 different problem types.
Sure.
One of them, they're both the challenge problems. So one of them is 2 reactions, 1 container, and the other one is 2 acids, 2 acid reactions, 1 container. And then there's another graded one that's just 2 reactions, 1 container. So it's like basically just 2 reactions, 1 container.
I should probably take those off of there, to be honest.
Yeah, it's like, I mean, they're pretty rough. I was looking at like,
They're pretty
what
rough,
do you do?
and-
There's so many elements and there's so many numbers there. It's like,
Yeah. Realistically, I should take that as like not being a graded problem. We changed some of our curriculum this year. I guess we actually changed it last year. But we used to all do 2 reactions, 1 container, full calculation with 2 equations, 2 unknowns, and
Yeah, I remember you
solving.
talking about that yesterday.
And we cut that out, but I didn't cut all of the problems. So I won't. That's extra credit problem.
One of them is graded, so that's why I was like.
It's graded extra credit. I'll take the points. I'll take that assignment out of 19 instead of 20.
And then, number 10 on that one as well. This one's more like something that we've seen before. I'm just kind of confused. It's like, it asks the empirical formula of the hydrocarbon that forms when, like, the CO2 and H2O are given. So you have to find the empirical formula while given the products, and that's why I'm confused by.
So let's go ahead and look at number 10 to get together. So that's another problem that I'm like, ooh, I should probably take that off. But it's actually not that hard. There's just like 2 steps to get to the problems that we're familiar with. So let's go ahead and look at that real quick. And then I'll just do the setup to the point where we get to the problems we've done before. And then I'll help 129 folks out some. So if we're looking at, that's 9.2, number 10?
Yes.
9.2, number 10. Go ahead and give me the masses.
It's 60.68 grams of the hydrocarbon, 89.12 grams of CO2, and 36.48 grams of water.
So here's the thing we have to figure out. And I actually love these problems. I feel like we should do more of them. I feel like I should switch back. So I like the, it's not the harder math, I like the more chemical thinking that's involved in this math, is really why I like it. How much of this 89.12 grams is carbon?
Or wait, no, less than that, because the molar mass.
32 plus 12.01 is
You're on the right track.
42.
So here's what we do. We take the mass of CO2, we times 1 mole of CO2 is 1638, oh, I can't do that in my head, 40? Is the mass of CO2 40? No, 50. Because it's 16 times 2 plus 12, 44. I was getting the wrong number. When I was doing 16 times 2, I was getting the wrong number.
It's like 60?
And then I can say 1 mole of carbon for every 1 mole of CO2. And then I can say 12 grams of carbon for every 1 mole of carbon. So you were on the right track. It's what percentage of CO2, what's the mass percent of carbon in CO2? And it's 12 over 44. So I do 12 over 44 times 89, and it gets me my percent of carbon. 12 divided by 44 times 89.12. And we get 24.3%. Sorry, not 24.3%. We get 24.3 grams of carbon in the CO2.
You can come in the center if you want.
Let's everyone just scooch over a little bit more. Bags underneath the desks and chairs so everyone can fit in.
No,
It's a lot of 124. This is a flip from what I usually have, and I'm loving it. Usually I only have like a single 124 student asking questions, and it's all 129, and it's a little bit opposite from that. So what we did is we said, hey, there's some portion of this mass is just carbon. So I divided by the molecular weight of CO2. I used the fact that it was a 1-to-1 ratio, and the mass of each carbon is 12, and I got 24 grams of that is carbon. That is to say, if I do 12 divided by 44, 27% of it was carbon, so 24.3 grams is carbon. I do the same thing with my H2O. So how much of this is going to be hydrogen? 2/16 of it, or sorry, 2/18 of it, or 1/9 of it is going to be hydrogen. Because there's 2 hydrogens, 1 oxygen, this weighs 1 each, this weighs 16. So it's going to be 2 out of the 18 total. So we can see that rather than just doing it in our heads, let's do this. 1 mole of H2O is 18 grams. Then we've got 2 moles of hydrogen for every 1 mole of H2O. Then we've got 1.01 grams of hydrogen for every 1 mole of hydrogen. And that will get me how many grams of hydrogen are there. So I do 36.48 divided by 18 times 2 times 1.01. 4.09. I make them do it. You don't remember? Wait, you had class with me, right?
Yeah, I remember it the Friday due day. It was terrible.
Yeah.
I wish it was due Sunday.
It's that again.
That's the only thing I remember.
I don't want to make people work on the weekend.
I'd rather do the.
I already do work for your class on the weekend. It doesn't matter.
I'd rather people getting ahead on the weekend rather than catching up on the weekend. Oh, well, okay. Let me double check my calculation. I got a little distracted there. I think double check is 4 grams, right?
What's wrong?
Let's see here.
Yeah, so you'll have the sigma 1s. It's gonna have to, because there's gonna be a total of.
Yeah, that's right. Okay. So
0, yeah, 2 total electrons.
you'll notice.
1.
Wait a minute. Wait, was this only carbons and hydrogens, or is there's oxygens too?
It just says hydrocarbon.
It's going
Yeah, I see the
to
problem.
increase
Yeah.
the length.
Well, it's combusted in the presence of oxygen. So that's why I was confused as well. So like, am I finding an O value or am I just finding a C and H?
Oh, it's read the formula in CXHYOZ. How did I know something was terribly wrong here? Right?
Because 24 and 4 don't add up to 16.
Yeah! I knew I was missing something. I needed that OZ. Because otherwise it better add up, because all of my carbon and hydrogen comes from my hydrocarbon.
So can you find oxygen just by subtracting those?
Yeah.
Okay, perfect.
So essentially what we've done is we've created a percent mass situation. So if I do 24.3 divided by 60.68, that's going to give me my percent carbon. And if I do 4.09 divided by 60.68, that will give me my percent hydrogen. And now we're right back to where we were with the problems we did in class. Can you go from there?
Yes.
Cool. I'm going to go ahead and pause the recording. And how about some 129 folks?